Hey, okay. All right. Thank you. Thank you for coming to this class and this lecture. Although it was not ideal weather today. It's good to see all of you. So, let's start this course, this LAC 3530, Integrated Analog Systems D. So lecture 01 is about introduction of this course. And my name is Kwante Kim, Aalto University. So let's start this course. All right. Okay. Okay. It looks good. Okay, so my name is Kwante Kim. I'm assistant professor at Aalto University. So my first name is pronounced like quantum. So if you're not sure how to pronounce my name, my first name is like quanta plus E, such as I'm not working on anything about quantum electronics, but it's interestingly similar to quantum technology. And we have three TAs, Jenhan Wang and Sujanya Bhomik and Wingyun Yao. Unfortunately, we couldn't find TAs in this room, but you will find it during the quiz and exercises. Okay, so this is disclaimer. Please note that the lectures will be recorded, including this screen, this one, and then my audio, such that all of you can watch them again if you don't remember what I spoke about something. And then videos will be available after this lecture. So if you have any questions, please scan this QR code. And you can also ask questions during lecture by interrupting me. But if you don't scan this QR code, it will show up later. Very like at least 30 minutes later. And then you can post questions to the Plasma platform. So if you ask question, then you can be answered by the next lecture. And the access code is this. Okay, so then let's move on to the introduction. And so we'll go through intended learning outcomes and real-world examples of analog mixed-signal integral circuits, introduction to myself and my research group, and get to know each other session. And we will check prerequisites to take this course, and we will have course overview, and we will go through the sampling theory as the first technical material. Okay, so this is the overview of our major courses, Microelectronics design course at Aalto University as a master's student, master program in electronics and nanotechnology. We can see that there are some classes about analog, like LAC E3120. And by the way, so we, as all of you know, that Aalto University has 5 periods, right? Period 1 is September to October 2025. Period 2 is October to December. And period 3 is January to February. And period 4 is February to April. And period 5 is April to June. So today is here, right? Today is January 7, and we have analog courses, 3 analog courses, analysis and design of electronic circuits, and basis of IC design, integrated analog systems D. This is this course, and here D means that PhD students can take this course. That means D. And other courses are there, such as digital microelectronics 1 to 3. If you are interested in digital circuits, and we have integrated RF circuit. If you are interested in RF circuits, and IC design project is there. It's a personal design project course. And within this year, the course names will be changed to Analog Integral Circuits 1 and Analog Integral Circuits 2. Okay, so let's go through this course. So this course name is Integrated Analog Systems, E3530. So I would like to make a subtitle of this course. So the subtitle is Interface to and from the digital world, such as how we are interfacing from analog world to digital world to analog, like this. From analog to digital world, from digital world to analog world. And then we are studying, or we will study about the interface between analog and digital. Okay, so but what is analog and digital? So that is the question. So do you have any clear idea how can you describe analog? How can you describe digital? Like, of course, you can think about like watches and clocks, such as a digital clock and analog clock. But let's take a very easy step. So when I asked the GPT-5 model, like generate an image to show difference between analog and digital, and this is what I got. For analog and digital, for analog, we have continuous signals, such as continuous time signal, continuous values of amplitude. I mean, it is represented as a continuous amplitude as a signal. Continuous signals include musics and temperature, volt, and light intensity. So continuous means that even if no matter how close you choose 2 points within these signals, how close it is, there are infinite numbers of points in between. That means continuous signals. On the other hand, for digital, I think it is a good representative diagram, although it is not 100% always sure, I mean, always correct, but it is a good catch-up. For digital signal, we have quantized world, such as for both of time axis, which is x-axis, and y-axis. For x-axis, we have sampled signals, which is quantized in time. We have quantized levels in the y-axis. That means quantized amplitude. So that both of them are mixed up, then it goes to digital circuit. I mean, digital signal. You can find such examples. For example, the data is represented with ones and zeros. That means, okay, maybe it's a digital. So our physical world is continuous analog indeed. So you can see that those physical quantities like music and temperature, I mean the audio signal, the temperature or light intensity, those are all analog. Such that, let's think about the situation. So when we are taking a shower, let's say when we are controlling the shower knob as a digital bit-step quantization, which is very large step, then it's going to be misery, right? So our physical world is analog, such that it will allow us to choose a step in between something that we are searching for. That is a very nice analogy. How do I say? Making distinction between analog and digital. And you may also think about this structure, such as, are we really sure our physical world is continuous analog? And when we go into, matter, like, just water drop, and we have molecule, and within our molecule, we have atom, we have electron and nucleus, neutron, and quarks, and so on and so on. Of course, but in this class, in our electrical engineering class and circuit design, we will stay in the classical domain in this lecture, such that our physical world is continuous analog. So this is the overview of signal processing circuits. So we have continuous time, discrete time, and continuous level and discrete level. So x-axis and y-axis, such that we are describing analog circuits and analog signals in general. Yeah, thank you. So in general, when we are describing analog signals, then you probably have mostly studied about the signals that is staying in continuous time in x-axis and continuous level in y-axis. This is a circuit. Like GM, here GM means transconductor. Like the course that you took, for example, at Aalto University bachelor level. So we have circuit analysis course, like C9110. And if we add a switch to control this analog signal, like with a very specific sampling frequency or switching frequency, then we are moving to discrete time, but continuous level, because we are not quantizing the amplitude, that it is still residing in continuous level signal, but we are going to discrete time. On top of this, so for this kind of signals, you probably have studied like a diode or RC circuit with switches that can be studied at analysis of electronic systems at C9120. And on top of this, when we add quantization, like quantizing purpose of time domain, purpose of amplitude domain, then we are moving to analog to digital converter. So ADC means analog to digital converter that converts analog signals into digital data. That is sampled with fixed frequency, and that is also quantized with quantizer. So in general, we call the upper two cases as an analog signal. We often call it, and we often call the lower, the other case, as a digital data. On the other hand, there is a remaining signal domain that has a continuous time, but discrete levels. So that kind of representative example is that when we drive a transconductor using voltage, and based on that current made of voltage, we are controlling the oscillator. This is called ring oscillator that has at least three inverters that is forming as a ring that generates oscillating signals. And this is normally called a time domain analog signal or asynchronous digital signal processing. So people call it sometimes differently, but you don't need to worry about it. It's out of scope, but it is good to mention. Okay, so let's go through intended learning outcomes. So what are we going to run in this course, intended learning outcomes? So for this course, we will understand the principles of continuous time and discrete time signal processing in circuits. We will go through to understand the building blocks of analog mixed signal integrated circuits. And we will learn to analyze and design analog and mixed signal integrated circuits using CMOS technology and CAD tools, computer-aided design tools, CAD tools. Okay, what about this lecture, today's lecture? So today we will understand why do we run. We have to think about and we have to understand why are we sitting in this room like from 8 a.m. Going through this snowy weather. And then why we are investing our precious time on this course. So we have to understand why do we run analog and mixed signal integrated circuits. And we will check whether you meet the prerequisites for this course. And we will understand why do we need an anti-aliasing filter. So we will talk about it and review some key concepts of sampling theory that you probably have run in prerequisite courses. Okay, then let's go through real-world examples of analog mixed signal integrated circuits. So this is an example, very nice example of analog interfaces in our world. Like probably many of you having this kind of AirPod. The earbuds, right? Apple's AirPod or Samsung Galaxy Buds. So it will allow us, we can talk to our friends through this AirPods, like by making call, or we can listen to music. We can even make commands to our Siri, right? So for this kind of device, it allows us to send or receive data through Bluetooth communication. And it has a microphone interface, such as not only about calling to our friends or calling to other people, but also it allows us noise canceling, right? So when we want to buy some headphones or earphones, we normally these days want to check whether this one has a noise canceling capability, then how good it is. To cancel out some noise, the first thing we need to do is, we need to first listen to noise. How much is noise coming or how the noise characteristic is there. And then we have to cancel out. So for that kind of purpose, of course, we need a microphone. And touch sensor, we can call, stop the call or stop the music or volume up, volume down the music, and so on can be controlled by this touch sensor. And we have speaker, of course. We want to listen to our music and we want to listen to other friends' voice through this AirPod, and more functionalities are there. So all of these are examples of analog interfaces in our world that is communicating or interfacing digital world within this device. So for this kind of Bluetooth receiver, let's say we are sending some data from our cell phone, let's say iPhone, and then we are sending music data to this AirPod. Let's assume that. Then our music data is sent to wirelessly to our antenna. This is a very generic architecture of Bluetooth receiver, wireless receiver. Of course, there are so many other variants and so many other different techniques that can be more state of the art, but this is very generic. Anyway, so this antenna can receive analog signal of the data that is sent to our receiver chain. That can be amplified by amplifier. And we have IQ mixers. Don't worry, this is out of scope. And then we have filter to filter out something. And then we have analog to digital converter, ADC. And then we have a digital signal processing. So going through all of this chain, now we are converting analog signals into digital data. So we have the intersection between analog and digital. Here, ADC. ADC is intersection. And then the main interest of this course is this, filter and ADC. So this is our main interest. And if you are more interested in IQ mixers and what are they, what are we going to do with this kind of device or circuit, then you can take integrated RF circuit course E3550. And this amplifier side, you can take a course of basis of IC design E3510. You probably have already taken the course. And for about microphone interface, the microphone, when we say something, then our microphone interface can capture our voice audio signal. And when we tear down our AirPod, then it can be seen that, okay, we have so many components, so many small things integrated nicely all together, right? And then when we want to find out where is our microphone device, then this is our microphone. This is a tiny, small thing. It's not a large thing, the microphone. Microphone is very, very small. And we can see that it is called MEMS microphone. And the front side, front view is like this, and back view is like this. So we can see there is a small hole right here. This kind of small hole can receive the voice signal through this hole, and our voice signal can be sent to this hole. And within this hole, our circuit is formed like this. We have MEMS microphone device that is biased with the biasing circuit, and we have analog buffer, and analog low-pass filter sometimes, and then analog to digital converter, ADC, and digital signal processing. And then again, MEMS structure, we will not study about this. If you are interested in, I will let you know the course. Anyway, so voice signal can be converted, all of these chains. In the end, it will be converted into digital data. And the intersection of analog and digital world is this. Again, ADC, analog to digital converter. And the main interest, again, is this, filter and ADC. If you're more interested in, then you can take ELEC E8715, Design and Analysis of MEMS-D. So this course, you can take it. Let me talk about the chip design companies in Finland that is relevant to analog and mixed signal integrated circuits. We focus, right? Bosch Sensortech, Otakari 5 and Murata in Banta. For Bosch, they are working nicely on analog circuits for acoustic microsystems. And Murata is working on analog circuits for acceleration sensors, and more opportunities are there. And you are probably interested in summer internships, right? So you can contact these companies, and you will probably be selected if you interest that companies. Then you will take the interviews, right? Then for that kind of interview, taking this course nicely and studying the materials about this course will be helpful. Okay, so let me introduce myself and my research group, which is T-Circle Research Group. So this is my short background. So my name is Kwante Kim again, and I obtained all of my degrees from South Korea, KAIST, bachelor, master, and PhD in 2015, 2017, and 2021. And after that, I spent multiple years as a postdoc and established researcher in me similar to senior postdoc position at ETH Zurich, Switzerland, and University of Zurich in Switzerland. I also was there. And since August 2024, I have been assistant professor at Aalto University, Finland, in electrical engineering, LI department. So this is our group. So we have tiny systems and circuits, T-circ group. We focus on circuit and architecture, algorithm, and system. And we have 3 PhD students that I introduced at the beginning as TAs. Jaehan is working on flexible integral circuits for analog circuits interface, and Sujanya is working on tiny neural networks algorithm side, and Lingyun is working on digital probabilistic AI accelerators. And we have past master students, Yu Xue and Kaiyang Jiang and Bingjang Chiu. Especially Bingjang is now working at Murata after his industrial master thesis project under my group. So let me introduce my research, focus in terms of application domains. So we are studying integral circuit research about biomedical sensors. So this kind of biomedical sensor has bioimpedance sensing. So bioimpedance can be measured by very, very fundamental principle of electrical engineering, which is Ohm's law, like V equal IR. So when we inject some small amount of current that is safe to inject, then we can measure our bioimpedance by measuring the voltage difference. Then we can calculate our bioimpedance by Ohm's law. And I have been working on neuromorphic audio signal processing, like I said, like audio interface, right? So when we say something, our voice signal can be captured by microphone interface that can be further processed through feature structure and DNN classifier. And through this DNN classifier chain, this is building audio keyword spotting, such as, what our speaker is talking about in terms of specific predefined keyword that can be captured by DNN backend. And the third one is flexible electronics. So this kind of flexible electronics has an EXO TFT chip-based process. So what is difference is that this kind of flexible electronics, especially provided by Pragmatic Semiconductor, it is a UK company, that provides some, device library that can be used to fabricate chip is flexible. So like it looks like the texture is kind of paper-like shape that can be easily attached to other curvy things. This is very nice. The problem is that, the challenging part is that it only provides N-type transistors. That means there are many, many opportunities to solve other problems that is remaining. So what is interesting, what is promising about this technology is that it has a low-cost fabrication. So it can go to green electronics and more, low carbon footprint, sustainable electronics that can be used for smart IoT fields such as smart ring and smart bandage and smart packaging. So recent activities under my group last year. So under my group, 2 master students worked with us, and nicely both of them presented their own publications at IEEE conferences. Like Yu Xue presented his own amplifier design, and Kai Yuan presented his own dynamic current reference, which is another analog circuit. And so it was very nice because this is a IEEE conference, which is good. Normally at Aalto University, sometimes PhD students present at IEEE conference. And both of them went to the conference venue, which was in Paris, which is good, right? And then they presented their own paper in front of international audience. And of course, they did a very nice trip, traveling through the central Paris, like museum and Eiffel Tower. And I think this is a Montmartre highlight. So anyway, if you are interested, please contact our group. So if you are interested in more about analog mixed signal IC design project during your master course, and join our group, you can work with our group. And please send your CV and transcript. Then we will review and contact you. Okay, so by this moment, maybe we can go through get to know each other session. So please form a group of 5 or 6 people and assign numbers to each person. And then introduce yourself to the group members and discuss why you are taking this course and what you want to run during this course. And a randomly chosen member will present a discussion summary. So we have 10 minutes. So until, let's say, 55. Go ahead. So the next thing we will talk about is prerequisites for this course. Yeah, I wanted to check what kind of interest all of you have for this course. I wanted to check like what are statistics in general. It's a basic class about statistics of all of you about like bachelor level or master level or IC design major or not. Because this course is a bit, how do I say, as I introduced at the beginning, this course name will be changed to Analog Integrated Circuits 2, which means if it's a bit advanced course than just a basic IC design courses. So let's check the prerequisites of this course that are really, really fundamental, elementary, and essential to understand what is going on during this course. So it is very nice to check. So the first prerequisite course is signals and systems, or equivalent if you are international student. And this is a bachelor level course. You probably have run continuous time, discrete time signals, and linear time invariant LTI system, and Fourier series, Fourier transform, and Laplace transform, and Z transform. So all of you have taken this kind of equivalent or similar course. Good. Any questions, please ask. And then the next one is circuit analysis or equivalent. If you are international student, it's again bachelor level course. Kirchhoff's law and series and parallel combinations, like how we are placing registers in series, in parallel, right? And Devon and Norton equivalent and nodal analysis, power and root mean square, RMS, and OPMs. The next one is analysis and electrical systems or equivalent. So this again, it is a finished course name. It's a bachelor level course, and it has a Laplace transform. How we are applying Laplace transform to analyze the circuit. And we have transient analysis, such as switching on and off, diode, and resistor, capacitor. And we have poles and zeros, and frequency response, and body plot. And first and second order systems, like first order filter, second order filter, and integrator, and differentiator. If you are not electronics and electrical engineering, major during your bachelor, there was another course for other people who are interested in circuit design, such as if you are robotics engineering major, then you can take this course to understand what is going on my PCB or something. So it's a very similar Kirchhoff's law and Devon and Norton equivalent and power and RMS, OPMs, and capacitor inductor impedance, and body plot and filters. And then we are moving to master level course, analysis and design of electronic circuits like diode and MOSFET, the transistor, MOSFET, and small signal analysis, and single stage amplifiers, and second order filters. For single stage amplifiers like common source amplifier, common gate amplifier, source follower, and second order filters, and feedback, stability, and phase margin. And basics of IC design, like in period 2 last year, right? So master level course or equivalent, it shouldn't be equivalent. The basics of IC design course. And small signal analysis, single stage amplifiers, again, is a common source, common gate, and source follower, two-stage amplifiers. And that goes to Miller compensation to stabilize the feedback loop. And common mode feedback, noise, and CMRR, and PSRR. So this is a very nice moment to check, to make our life easier and our life more happier. Like if you find the prerequisite courses or topics unfamiliar, then it is not recommended to take this course. It may not be your best choice. So it will be very hard to follow the contents because it's a bit advanced. I mean, if you take all of the previous courses, then it's fine. You don't need to worry about that much. But it may not be your best choice. Or if you are genius enough, then you can follow up during the course. But I'm just clarifying that it is not recommended. But if you find prerequisite topics familiar and feel ready, like 100%, or let's say not 100%, like at least 80%, let's say, then you will gain higher confidence in analog and mixed signal circuit design by the end of this course. Okay, so if you have any questions, then you can interrupt me during the course. Or if you already scanned the QR code, you can also ask questions. So this is course activities. And we will go through lecture for 2 hours in every Wednesday. And we will have quiz for 20 minutes. It's about traditional mini exam. So this is a bit different if you have taken basis of IC design. The traditional means that the quiz will take place 1 week after lecture, such that the quiz for lecture 1 will be taken after lecture 2 next week. And pens and calculators are only allowed for fair assessment. That means no cell phone, no computer, no ChatGPT, anything else. Submit the quiz in person during the class within 20 minutes. So the late submissions will not be accepted, but it is fine because if you're not happy with the quiz result, you can retake. You can request the quiz. You can ask TAs. Then we will schedule a retake of quiz. But the questions will be different for fair assessment. So like there is no limit the number of quiz retakes. So if you can study more and then retake the quiz, is fine. And then of course this lecture is under recording, so you can watch the videos later to study. And we have CAD exercise, 1 hour in class. In-person TA support will be provided only during the in-class session. So you may also continue working at home. You can use AI in this case. Even like electrical engineers or circuit designers these days extensively use AIs. Of course, we shouldn't rely on too much, but we are making use of it. And in-person TA support means that if you finish, like for example, by tomorrow, will TA support not available? No, you can contact TA through my courses website, and there is a discussion forum. You can ask questions there, and our TAs will try their best to answer the questions. And project is about final exercise. A circuit design project, it will be, and you will choose one topic for your project. We will provide some topics, at least 2 or 3. Teaming up or maximum 2 is encouraged, but it's not mandatory. So teaming up is fine. And if you think of more team members are required, then you can request. Then we will discuss. And you can also use AI. And this is the remarks on exercises and project. So about AI usage. So AI is allowed, but we strongly recommend and encourage to use it to clarify concepts, not to generate solutions. So please build your own independent understanding first. And about collaboration, about like quiz or exercises, the collaboration is fine. This is encouraged. Discussing ideas with peers is encouraged, but copy and paste from other colleagues is not allowed, prohibited. Your submission must reflect your own work, so your own understanding, your own study. And about your career preparation. So after this master degree, right? After this master course, you will be awarded master's degree. Then before your master degree, you will try to find out like working place, job opportunities, career. So authentic effort now is the best preparation for technical interviews, like and your future career. So please try to understand yourself and study. And relying on shortcuts today may limit your success tomorrow. So if you try your best for understanding and study, then it should be good. Then it should be good to prepare your future career. And this semester, the course will still be under construction. So we will make sure every week has their own lecture formulation and C8 exercises. So significant updates to course materials are ongoing. And we would be greatly appreciated for your patience if any delayed or interrupting or any problems may arise. But we will try our best. So this is assessment criteria. So we will have project 40%, quiz 30%, and CAD exercise 30%. So let's have a break, and you can also take your time to take that gum if you feel it'll be helpful. You can post questions to the Press Demo platform and scan the QR code. This is an access code, and selected questions will be answered in the next lecture. So we will have break until 15. And can probably move to the next part of today's lecture, which is sampling theory. So now we are jumping into more technical side of this course. So okay, let's have a look on this microphone interface that I have introduced earlier, AirPod, right? And when we are saying something, then our microphone interface can capture our voice signal or audio signal that can be converted out of these chains into digital data. And I would like to ask a question. I mean, it is all about converting analog signals, audio signal into digital ones and zeros. But I mean, why do we put a filter, by the way, here? It's about, sorry? You get it. It's good. Yeah, but I will go through as a recap, reminder of what we have learned. Sorry. Actually, I have prepared chocolate if you participate to the course as a energy. But why do we need a filter, by the way? That is a question I'm going to answer during this course. Not course, lecture. Okay, so this is a recap of signals and systems you have probably taken as a bachelor level course. And let's say we are nicely having this sinusoidal input as a input audio signal, for example, or wireless Bluetooth signal. Then we are doing sampling. Then like what we are doing, like photographing, taking picture. Then the sample signal will look like this. It has a sample signal like this arrow shape. And then it will be like this after sampling with a fixed time window. Then in mathematical transformation or expression, we can express this situation using these equations. And the input signal is xt, and the sampling is indeed multiplying the input signal with impulse train. The impulse train errors are multiple errors, infinite errors are taking place every single time when we are doing, taking picture action. Then the resulting signal, let's call it as a XS sample, T, let's say. And then let's call impulse train as a PT, a small letter here. Then what we are looking at as a mathematical expression is this kind of impulse train can be formulated with the unit impulse function. If you remember this, what it is. So this is a direct delta function in continuous time domain. And direct delta function is expressed as a limit by making this large delta to 0 like small delta, large delta t is kind of weird to pronounce. Anyway, so this kind of approximated Dirac delta function can be expressed with the value of 1 over large delta if absolute time is less than large delta over 2. Otherwise, it's all 0. So let me try to describe this. So like using pen, then we have time here. Then it has like this kind of rectangular shape. The value is 1 over large delta. And here is large delta over 2. And here is negative large delta over 2. Such that the area under here is always 1, no matter how large delta is small. Such that this kind of Dirac delta function is actually approximating this kind of unit impulse function. I mean the approximated Dirac delta function, as it takes like this shape or higher, even higher. But we are approximating this function as just one arrow, such that it normally means that mathematically, it means that it has an area equal to 1 at time equal 0. And then when we think about this impulse train, then this kind of impulse train is summation of like unit delta function, Dirac delta function at t minus sampling period. Let's call TS, large TS, as a sampling period. Then sampling time window plus delta t minus 2 times sampling window plus the delta t minus 3 times sampling window plus and so on and so on. It's infinite numbers of it. This is an infinite number because it is assumed that we are always taking, like forever, taking the pictures. So mathematically, it is expressed as a small pt is equal to summation from n equal negative integer until positive integer infinite. And delta t minus n times sampling period. So n spans from negative infinite integer to positive infinite integer, including 0. And now it is good time to take a look from time domain to frequency domain. So like, for example, if we are mixing up many large signals or high frequency signals, small low frequency signals mixed up together, it is very hard to analyze in time domain. So what we are choosing for circuit analysis, we take frequency domain analysis. For this, you may have learned during signals and systems course about Fourier transform. And is there anybody who still remember what is a Fourier transform result of this impulse train? Come on, try to remember. What was it?
Remember, but it is a multiplication instead of a sum.
Multiplication of
something like this. I remember. I can't remember now.
Oh, so you mean instead of this summation, there's a multiplication?
Yeah, I remember something like that, but not something really concrete.
Yeah, good try. Or anybody else have different idea?
Maybe I'm switching it up with the Laplace transform, but wasn't the Fourier transform used to like split a signal into different smaller signals? So for example, if you have overlapping frequencies, you can disassemble the signal into each corresponding, I think, sinus curve squares.
So when you take the sine wave as an input, when you do the Fourier transform, then in frequency domain it has like this.
Yes.
Or cosine it like this. So it was a good try, but it's a bit apart from the correct answer. But I would just say gratitude here. Oh, sorry, here. It's energy. So the answer is same. The same formation, I mean, same structure. The Fourier transform of this impulse train is again impulse train. It's still in frequency domain. So you can find the exact proof of this derivation by finding chapter 7.1 of this book, Signals and Systems book. And yeah, so we have large P J omega equal to 2 pi over sampling period multiplied with summation. K spans from the same infinite span for summation span. And then delta, now it has a frequency domain representation, omega minus K times omega S. Here, omega S is angular frequency, 2 pi times Fs, sampling frequency. And the sampling frequency is equal to 2 pi over Ts. So F equal to 1 over T, right, in physical dimension. So it will look like this. So large P J omega will look like the impulse train that is spaced. Now it is converted from sampling period Ts to omega S, which is a spacing in the unit space, right? And then actually, this is what you have probably run during the signal resistance systems, mostly staying within the J omega domain when you apply Fourier transform. But circuit designers typically use frequency notation instead of angular frequency. So F equal omega over 2 pi. And when we apply this kind of concept by converting this equation into this large P, now it is F domain, not omega domain. F domain is equal to 1 over Ts times a summation of K spans from negative infinity positive infinity delta F minus K times Fs. Here Fs is sampling frequency. And for this, you can recall the scaling property of delta X, the unit or Dirac delta function. The delta omega becomes delta 2 pi times F, and it is converted into 1 over 2 pi times delta F. And this can be derived by using the definition of unit impulse function. So by applying this, we can easily figure out, okay, now PF equal to this equation. So yeah, we have now the same notation, like impulse train in frequency domain, but spaced with Fs instead of omega S, sampling frequency. And in general, when we apply Fourier transform in F domain, we have equation like this. Xf is equal to integral negative infinity to positive infinity xt times e to the minus j omega t dt. And the inverse Fourier transform, we can reconstruct the original signal using this equation. Xt is equal to integral minus infinity to infinity large xf e to the power of, now we have negative j 2 pi ft df. I think I have a mistake here. Not omega, is 2 pi f here, because we are representing in F domain. So if you are interested in more, then you can take a look at this book, Signals and Systems book, and find chapter 4.1. So anyway, we have XF. For example, let's say this is not the mere sine wave signal, like more complicated audio signal, let's say. Then the frequency domain shape, let's say it has a kind of this bell-like shape. And let's say input xt's Fourier transform is represented as a large xf. Then the question is this. So what will be the result if we multiply together like xt and impulse train in time domain, and when we do the Fourier transform to have a look at it in frequency domain, then what will be the result? Any idea? Small idea? You can try. By the way, this is all you probably have run during the course of Signals and Systems course. It's just merely you just forgot after a long time.
It will be like the, let's say the original sampling, but it will be all on the upper side, and it will have also, let's say, 2p multiplies.
2p multiplies.
I think.
Oh, that's similar. That's very similar. That's very close. So you can get another chocolate. Here. So it is very similar. I mean, it is not, let's say, it's very close to the exact answer. Then let's take a look on mathematical expression about this. So if you remember, then when we multiply in time domain and when we take the Fourier transform, then it will become convolution in frequency domain. So we call this multiplication property of Fourier transform. And vice versa is also true, such that when we take the convolution in time domain and when we go through the frequency domain, such as using Fourier transform, then we end up with multiplication in frequency domain. So that is called as a convolution property of Fourier transform. So let's have a look at this equation, such that we already have large P F, right? And large P F will look like this. Summation, sigma k equal blah, blah, blah equation. Then we can substitute, plug in this equation into this. Then we have 1 over Ts and xf convolved by delta f plus delta f minus fs plus and so on and so on. Then indeed, if you remember, when you convolve any signal with delta function, right, or direct delta function, then it results as the same signal. If we convolve some signal with delta function that is time shifted or frequency shifted, then it will result as an original signal that is time shifted or frequency shifted. So we have xf plus xf minus fs plus xf minus 2 times fs, and so on and so on. And the result is this. So 1 over Ts, sampling frequency, sampling period, times summation, k spanning from negative integer infinity to positive integer infinity. And now we have large X, f minus k times sampling frequency. So what it will result is this. So we end up having repetitive replicas of xf. So basically, it is just copy and paste, copy and paste, copy and paste in frequency domain after sampling, but it is spaced by this unit sampling frequency fs. That is the result, right? And that is very highly relevant to what you probably have talked about, anti-aliasing. So we will go through it. So the equation will look like this. Then there's another property that we have to think about. If you recall correctly, then signals and systems course, like chapter 4.3.3, and if xt is real, like real means a physical quantity that we measure in our real world, then the frequency domain after Fourier transform, its magnitude is even function. So you can have a look how we derive this proof. Anyway, the even function in frequency domain, it means that its magnitude over the negative frequency is equal to positive frequency. That is the definition of how we call even function. So it looks like this. It's a mirror twins. Like over the f equals 0 hertz, it has a negative frequency. It is exactly the same as a positive frequency. So it will look like this if we measure our real signal. So indeed, if it is the same, then why don't you fold it up and then express in frequency domain in positive frequency only? Then we go to 2 times amplitude, such that normally we call in circuit design world, we call our left side as a double-sided spectrum and the right side as a single-sided spectrum. Very typical in analog circuit design. But sometimes when we have to analyze very complicated concept and sampling concept, then we have to go back to double-sided spectrum. But this is easier in most of cases for analog circuit design or analog circuit analysis. So now it becomes like this. okay, it has X signal in frequency domain XF, and the impulse train also represented as a single-side spectrum, and the replicas of this sampled signal, which is XSF, is also represented in a single-sided spectrum with the spacing exactly same as sampling frequency. So aliasing actually causes irreversible distortion, if you remember the course of signals and systems, in the sample data. Such that, let's say, when we have bandwidth, the input signal's bandwidth is large enough or high enough, then it is, as we discussed here, it is basically copy and paste in frequency domain that is spaced exactly same as sampling frequency. But that means if this bell shape is quite wide enough, then we will end up overlapping aliasing, right? So if XF has a too wide bandwidth, let's say F bandwidth, then it will cause aliasing. The other case is also possible. Let's say we fix bandwidth, but we suddenly taking pictures, the pictures sampling frequency or picture speed is reduced. Then the sampling rate fs is too slow. That means, okay, we are copy and paste the original signal with much less spacing. That goes to aliasing again. So here we comes Nyquist theorem. So it is important to make sure Nyquist criteria such that we have f bandwidth here and the sampling frequency here, the spaced, and the sampling frequency is a spacing factor, right? Then this right side edge is actually fs minus f bandwidth. Such that to make sure these two bell shapes are not overlapping each other, then we have to make sure, okay, this f bandwidth is less than fs minus f bandwidth. That goes back to the same equation here. Fs must be larger than 2 times f bandwidth, or f bandwidth must be smaller than fs over 2. So we call this specific term, fs over 2, as Nyquist frequency. F Nyquist equal to fs over 2 in circuit design field. And in reality, actually, so even if, let's say, we make sure the bandwidth of input signal is always smaller than Nyquist frequency, fs over 2, in reality, there is always noise. As you probably have run back in basics of IC design or any other courses, then you can easily find there is a random noise. It is spanned over very, very wide frequency, over f bandwidth, such that we cannot avoid this kind of random noise if it spans over really, really wide frequency. That means we are actually not satisfying the Nyquist theorem, right? It's already over the Nyquist frequency. So what will happen is that, okay, we are copy paste of all of these signals, input signal plus noise. That is copy and pasted because we are sampling with this equation, right? Summation. Such that noise is accumulated over copy and paste and copy and paste. That means we are ending up with very, unfavorable noise floor increase. This is an aliased noise. So it is not good. So what typically people are applying is, now it comes anti-aliasing filter. So we don't want this kind of noise level is increased a lot, such that, let's say, without this kind of anti-aliasing filter, no matter how clean we speak, then when we use the Apple's AirPod, the other person we are calling to will hear a lot of noise, background noise, random noise. So anti-aliasing filter, mostly it is a low-pass filter, but there are some other advanced techniques such that to build a band-pass filter of anti-aliasing filter or high-pass filter can be possible. Anyway, so we don't want this kind of random noise to be aliased. So after filtering out, we can see that, okay, it has aliasing-free sampling. So this is it. So we need a filter anyway for anti-aliasing because we don't want this noise level increased too much. So let's say we have input signal, audio signal, but we also have random noise anyway. So without filtering out this noise, we end up aliased noise. That is an increase of noise floor. So we need a filter for anti-aliasing. And here is a fun fact. Anti-aliasing in graphics, if you're interested in graphics engineering and digital circuits, then there is a concept of anti-aliasing if you play video games. And anti-aliasing in graphics is not equal to anti-aliasing in signal processing. So don't be confused, and let's play the video.
Jagged, those ugly stair-like patterns on diagonal lines. That's called aliasing, and it's every gamer's nemesis. But don't worry, we've got a solution: anti-aliasing. Think of it like your names. Anti-aliasing smooths out those harsh edges by blending nearby pixels together. There are different types of anti-aliasing. FXAA is fast but a bit blurry. MSAA is sharp but demanding. And TAA is the new kid on the block that uses data from previous frames. The best part, modern games let you choose what works for your setup. Higher NPC, crank up that MSAA budget build. FXAA has got your back. So next time you're in your game settings, remember, anti-aliasing is your friend in that fight against jagged edges.
So it's not relevant to anything about the jagged edges. It's about signal processing. So anti-aliasing filter, what we are talking about is doing something before we do the sampling. So what they are talking about, the anti-aliasing in graphics, is doing something after something happened. That is a post-processing. We call this a pre-processing. Okay, so now it's a funny part of aliasing demo. So you can make a form of group as you grouped earlier. And scan this QR code, or if you turned on the computer, you can go to this website. I think this is not difficult that much to type in keyboard. And yeah, so let's go to this website. Okay, if you go to the website, then you can find aliasing demo. We are still recording nicely. Let's make it hide. Okay. Is there anybody who find difficult to find this website? Everyone found it? Okay. Then, with this demo, I'd like to go through. I'd like to go through this. Under what conditions? Please try to answer. Oh, sorry. So let me show you how do you use this one. So, for example, we have RPS number we can put such as, for example, here we are currently RPS equal to 1, right? The RPS, it means that rotation per second. And FPS, it means frame per second. So this screen has a 60 FPS, such that its frame rate is 60. And when we put number 2, then you can see that its rotating speed is increased, right? And if we put 4, it's rotating even faster, right? So you can play in this way. And then let me go back to our slide. So let's try to find out the conditions. Under what condition does the clock look like sample only a single point, or sample only 2 points, or sample only 3 points or 6 points? Please play a bit. We can have 3 or 15, 3 or 5 minutes. You done? Okay, then we will check later. Cool. Okay, was it easy enough? Is there anybody who couldn't find the correct answer? No? Okay, then we can move on to figure out what is happening here. So aliasing demo, and yeah, so probably you have found the answers already. So in physical quantity, we have a phi, phase is equal to, in physical quantity, 2 pi ft plus phi 0, right? So here, f means frequency, and t means time. So frequency, it means a cycle per second. It's a mathematically concept. And the frequency is, in our case, is actually the rotating frequency. It's that how many rotations are this clock, is this clock making, right? That means RPS, rotation per second. That is the speed. So that means the frequency is actually F equal to RPS, right? Rotation per second. And the time, indeed, is a sampled values. In our case, is a dimension of second, right? Because our screen is refreshing with certain frame rate, such that the frame rate is here, FPS, right? That means the frames distance between two adjacent time frame, it goes to 1 over FPS. And we can assign number n here, and it's integer. This is very similar when we try to plot something in MATLAB or Python, sine wave. So it goes to, the plugging in both of equations here, and it goes to phi equal 2 pi n RPS over FPS plus phi 0. Then what it goes is that sample only a single point. Did you find it? Was it easier?
Single point is sampled at 60 at a rate of 60 replications per second, since the frame rate is limited to 60 frames per second.
Yeah. So was there anybody else who found out? The FPS is not equal to 60. So all FPS was 60, right? Oh, 90. So you got a better cell phone or fair screen. Sorry? It's fine. Okay. Anyway, so it doesn't mean something is wrong. So FPS means how fast it is your screen. So anyway, yeah, it's correct. So if we set RPS equal to FPS, such that when the FPS is equal to 60, then when we set RPS equal to 60, then it goes to staying at single point, or FPS equal to 90, then we can set RPS equal to 90. What happens in mathematical format is that when we make RPS equal to FPS, then this fractional term becomes 1. Then it goes to 2 pi n plus v0. In mathematical domain, is equal to v0, right? Because 2 pi means rotating 360 degree. So no matter how many numbers of integer numbers of 360 degree, it's always staying as v0. And what about sample only 2 points? Did you find out?
Yeah.
Please go ahead.
Was 30 rotations per second.
30.
Since it's the half of the frame rate of
the
screen.
Half of the frame rate, right? Half of the frame rate. And when we figure out in mathematical format, then we can get RPS equal to FPS over 2, right? When we plug in this equation, then we can get pi n plus v0. That goes to v0 or pi plus v0. Why? Because let's say we are starting from here, then pi degree rotation, it goes to 180 degree. Pi amount of rotation goes to 180 degree. Another 180 degree, it goes back to the original base. That goes to alternating 2 points. So what about arbitrary k points, like 3 points or 6 points? Then we can simply dividing FPS over some value, k value. that can go to 2 pi n over k plus v0 if k is integer. That is the question. That was the question. Okay. Thank you for participating. All right, then under what condition does the clock appear to rotate at RPS equal to 1 in clockwise, even though RPS is not equal to 1? Can you answer this question? And what about going counterclockwise at RPS equal to 1? What about counterclockwise while alternating between 2 points? And do we understand why? That is the question. Please go ahead. Okay, then probably we can go through the answer of this activity. Okay, so let's recall our aliasing principle, right? So to make sure aliasing doesn't happen, then we have to make sure Nyquist theorem is satisfied, such that sampling frequency must be larger than 2 times f bandwidth, or f bandwidth must be less than Nyquist frequency. Here in our case, f bandwidth is equal to RPS, the signal speed, and the fs is equal to fps. So Nyquist frequency is half of fps. And then let's go through this. So for clockwise, even though RPS is not equal to 1, but it will look like RPS equal to 1 case. Then how did you make it?
61 rotations per second.
61.
61, yeah.
Yeah.
Since it's an entire rotation and something more, so it's equal to 1 in this case.
Equal to 1.
From the simulation aspect.
Did you find other cases? Did you find all the 61 case?
Yeah. Any more?
Plus 1, right? Yeah, exactly the same. I mean, it was correct. So if we set RPS equal to 1, let's have a check. Conceptually, it will happen like that, but it's also good to know in mathematical information. So mathematically, when we plug in RPS equal to 1, then it goes to, so let's say left clock as a 2 pi n over fps plus v0. And what about RPS is equal to fps plus 1? That means fps, the always 1 rotation completed plus 1. Then it can go to v left or v right, right clock equal to 2 pi n fps plus 1 over fps. This part is cancels out as a 1, and it becomes 1, and then it cancels out because it is equal to 2 pi n, such that it results it ends up with 2 pi n over fps plus v0. As we recall, the Nyquist theorem makes this condition. In this case, left clock and right clock are indistinguishable. So that means this is because of that happens. This is happens because of aliasing. So we have 61, right? No matter how big it is, such that when we plug in 10, that's too fast, too much, 5, and when we set 65, and when we restart clock, it becomes same, right? And then what about the other case? Let me go back to laser point. Okay, so about counterclockwise, when we plug in RPS equal to FPS minus 1, then our equation becomes like this: 2 pi n FPS minus 1 over FPS. Then this part again cancels out because this is 2 pi n, and it becomes negative 2 pi n over FPS plus v0. So in our case, Nyquist theorem is still not satisfied because this is over speed of Nyquist frequency. And in this case, left clock, right clock travel the opposite direction with the same absolute velocity. This is because of aliasing. And then let me go through this experiment such that here we have set 5 and 65, right? So our FPS is equal to 60, such that when we set 55, oh, it's very hard to see, right? Let's go back to our low frequency. Let's set 0.1 and 59.9. And when we reset the clock, then we can see it's rotating the other direction, right? And we will figure out why this happens in both of mathematical expression as well as taken frames in the next lecture. So this is it for today. Thank you for attending this lecture, and we can stop here for a lecture, and we can move on to CAD exercise after taking 10 minutes break. Oh, if you have a question?
One question regarding the quizzes. With our notes or without our notes?
Note.
Yeah, I mean, when I study, I make my own notes. Do I have them with me or not?
No. So only, sorry, let's see. The personal note.
Yeah.
Let's restrict to 1 page then.
Yeah, of course.
1 page.
So,
yeah, 1 page is allowed. And then pen, and if you need, calculator. That's it. But the quiz will not be super, difficult
yeah,
to.
Thing is just the formulas.
Formulas. Yeah.
I'm very real.
Cool. Okay.
Is it 1 page or the both sides of the page?
Both sides. Both sides of the 1 page. Okay. If you have any other question, please ask. All right, then we can move on to CAD exercise session. Thank you. Probably we can start CAD exercise after breaking 10 minutes. So we will start from 10:30.